Kia ora koutou, no mai, haere mai. Welcome to lesson 24 for introductory physics. This is the third and final lesson for the thermal physics section, and we're going to look at two different things today. We're going to look at phase changes initially, which we've already sort of mentioned in passing, and then we're going to look at some calorimetry problems as a whole, which will incorporate the things we've looked at so far in thermal physics. As usual, we'll jump over and talk through the slideshow for the bulk of the lesson. Our learning outcomes for this lesson are to be able to state and define the different phase changes, and so that involves stating the different phases and then the changes that can occur between them. We want to make sure we understand what's going on at the molecular level during these phase changes. Again, we've sort of already mentioned that, but we're just going to make sure we state it explicitly now. We're going to talk about how phase changes can actually heat or cool an object. And we're going to calculate the energy required for heat and phase changes, which will lead us into solving calorimetry problems. So that's our goal for this lesson. First of all, though, phase changes. We're familiar with the different states already, and when a substance changes from one of those states to another, that's called a phase change. That's all it is. So a phase change requires heat being applied to a substance to overcome chemical bonds between atoms and or molecules. So the translational kinetic energy of the molecules is not actually increasing when this happens. Remember the idea of a solid being made of a whole bunch of atoms all held together by little springs, but the springs are actually bonds between the atoms. And when you give it enough energy, enough internal energy, it tries to increase its translational kinetic energy. It tries to vibrate or jiggle around a bit more inside its little space that it has. And once it gets enough energy, it will break those bonds. But breaking those bonds takes energy. So when that happens, it actually ends up not having more kinetic energy than it had before it broke those bonds. It uses the extra energy to break the bonds. So once a substance gets to its melting point, once it's got enough energy that more will break those bonds, that extra energy that you give it doesn't go into raising the temperature at all. It goes into that bond breaking process. So that while a substance is changing phase, the internal energy is increasing, but the temperature is not, because the internal energy, the chemical bond energy, the energy used to break those chemical bonds between all of the atoms, that's increasing. But the temperature, that translational kinetic energy, that doesn't increase, because by the time they get to that melting point, the atoms basically say, any extra energy you give me right now, I'm just going to use to break all these bonds and become a liquid. And so it doesn't use any of it for translational kinetic energy. So before its phase change, before the melting point, increasing temperature the whole time, constantly give it more energy, increase temperature. Once it reaches that phase change temperature, that melting point, then the energy you give it just goes into breaking all those bonds. It doesn't increase the temperature at all. Now remember that temperature is an average value. So some of the atoms might get slightly higher temperature, but then you're going to collide with ones that are still part of the solid and lose that energy to those atoms, which will use it to break the bonds. So on whole, the average temperature will stay at that melting point until almost all of the substance has melted. The same thing happens in reverse. If you're cooling something down, if you're taking energy off a substance, then as it cools down, as it gets to its freezing point, which is the same as the melting point, just going in the opposite direction, as it gets down to that freezing point, so liquid molecules are slowly cooling down, when they bond, they give off a bunch of energy. Right? And when they bond, they give off that energy, but their kinetic energy hasn't dropped. Their translational kinetic energy hasn't changed. They've just given off some energy due to the formation of that chemical bond. Right? So either way, whether you're heating up or cooling down, melting or freezing, the internal energy will be changing the whole time. But if you're melting or freezing, the temperature won't change. And when you are getting a change in temperature, it means you're not yet at that melting or freezing point. For a solid and a liquid, if you solid going into a liquid is melting, liquid going back into a solid is freezing. You are probably familiar with those words already, but I've just included them for completeness. The amount of energy a substance needs to do that melting process, to go from a solid to a liquid, that is called the latent heat of fusion. Latent heat of fusion, to go the other way and freeze a substance. So we said you need to give it energy to break all those bonds, and 1 kilogram will need some amount of energy to turn completely from a solid to a liquid. To go the other way, if you take that kilogram of liquid and turn it back into a solid, that'll give off that exact same amount of energy. It's perfectly symmetrical. There's no energy gained or lost as a whole overall. We've still got conservation of energy as a whole process. So the amount you put into the substance is the exact amount it will give off when it freezes again. The latent heat of fusion units are just the amount of energy per kilogram of substance, so joules per kilogram. As with specific heat capacity, you'll often get other variations on these units. So it might get kilojoules per kilogram or calories per gram, things like that, but it will always be an amount of energy per some unit of mass. Remember, there's no temperature change. While it is changing phase, it stays at the same temperature, so there's no temperature unit in our latent heat of fusion, nor in our phase change energy calculations. Some examples here: aluminium, 396,000 joules per kilogram, copper 206,000, gold 63,000, and water 334,000. So the water latent heat of fusion is not specifically high or low, but remember the specific heat capacity of liquid water was very high. But for the latent heat of fusion, there's nothing unusual there. It's pretty standard compared to other solids. Liquid and gas. When liquid changes to a gas, we call it vaporizing. So we say it is vaporized. When a substance goes the other way, a gas condenses into a liquid, we say it has condensed, right? Condensed into a liquid. Evaporation is a term we're often familiar with from our everyday life. So what is evaporation? It's just the name given to the process of vaporization. It's the same thing. You can say that it's evaporated or that it's vaporized. They mean the same thing. In everyday language, evaporation generally refers to vaporization occurring when the ambient temperature, the atmospheric temperature, is not at the boiling point of the substance. But evaporation as a term in science just means the same thing as vaporization. And so we've seen that. We've seen puddles that evaporate during the day. The sun's shining on them, even though the air temperature is still well below 100 degrees Celsius, thankfully. The water in the puddle will evaporate, right? It somehow manages to change phase from a liquid to a gas. So what's going on? How can we have this change in phase even though we're not at the boiling point for water? Remember that the temperature is an average of the kinetic energy. It's a measure of the average translational kinetic energy of all the water particles in that puddle of water. And the water might get quite warm because it's a thin layer and it's on the concrete and it absorbs quite a bit of the sunlight coming in. Remember that whole idea of absorbing versus emitting. And if it absorbs more than it gives off, then it'll warm up. So the water might get warmer than the surrounding air anyway. It's not limited to that temperature, but it still certainly won't get to 100 degrees Celsius. But as it does get warmer, as it heats up to maybe 30, 40 degrees Celsius, even though the air around it is only high 20s, some of those water molecules will get high enough to be able to escape. A few of them will get high enough that they can break their liquid bonds and fly off as a gas. That's because, as I said, temperature is an average, which means we've got a distribution. We've got some really cold molecules, some really hot molecules. The substance as a whole, we measure the temperature as the average of those. So the ones with enough energy might get enough to overcome all those bonds and escape and become a gas. They evaporate. And as I said, that's what we often use the term evaporate to mean in everyday life. We'll often say boiling when we deliberately bring a pot of water to 100 degrees Celsius. We call it boiling. We've taken it all the way to its boiling point and then we keep giving it energy and it evaporates off. Evaporation, we often use just to mean when the surrounding environment is not actually at the boiling point of the liquid, but some of it still manages to escape into a gas. If the molecules with the highest kinetic energy are leaving, then that means the average temperature, the average kinetic energy of all the molecules that are left has gone down because you've taken the highest ones and got rid of them. And that's left everything else that was all lower than those highest ones, so the average has to decrease. So evaporation will actually cool the entire pool of water. You lose a few molecules, the highest energy ones, then the rest of them on average have a lower temperature, and so the effect is that the temperature of that water appears to have decreased. In reality, the energy of all the other molecules hasn't actually changed. I mean, we know it is constantly changing as they collide into each other, but the temperature of all those other molecules hasn't changed. You've just taken out the highest energy ones. So the whole body appears to cool down. And that works with us as well. When we sweat, that's the whole point of sweating. When we sweat, the highest energy water molecules evaporate off of us, taking a whole bunch of energy. And it leaves us with a slightly lower average temperature afterwards. And that is why we cool, that is why we sweat to cool down. Dogs do the same thing when they pant. They pant so that they can cool down with the highest energy water molecules evaporating off their tongues. Just to hopefully drive this home, I've done a little illustration just with a really simple few molecule substance, whatever it happens to be. We've got two molecules with one energy. I'm not worrying about units, we're talking about the magnitude and the idea of this cooling effect. 4 molecules with 2 energy, 5 with 3 energy, 4 with 4 energy, and 2 with 5 energy. So that produces the graph on the left there, or in the center of the slide. And we see that it's a distribution, it's just sort of a curve. And that is roughly what the curves look like. They will always look like the bell curves that you're familiar with. They'll look something like that. And so you can see our average is right in the middle there at 3 energy per molecule. However, if we get the top 2 to evaporate off, say that 5 energy is enough to evaporate, then what we're left with is the rest of them. The 2 molecules at 1 energy, 4 at 2, 5 at 3, and 4 at 4, and the average is now only 2.73. So the average has dropped from 3 down to 2.73, and the overall temperature will have dropped accordingly as well. So evaporation is a cooling process. In the same way that some molecules of a liquid have enough energy to escape and become a gas, some molecules of a gas end up with low enough energy that they can condense into a liquid, even if the overall temperature of the gas is enough to remain a gas. One molecule cannot be a liquid. So this is just a little language point, a language note for you. The term liquid means multiple molecules bonded together in some sense. Not the same bonds as we get in solids, remember, but it just means they want to stick with these other liquid molecules. So you can't have a single molecule and call it a liquid, because that liquid requires multiple molecules. Because the lowest energy molecules in that gas will condense and form the liquid, that means the same thing as we saw with evaporation, the average temperature will change. In this case, you're taking out the lowest energy ones, so your average temperature is going to increase. So condensation is a warming effect, evaporation is a cooling effect. The other way that condensation can occur, rather than just a few of the gas molecules getting low enough energy and colliding and forming a little droplet, which is what the previous type of condensation we were talking about was, the other type that can occur is when there's already some liquid in the area, in the environment, and one of the gas molecules collides with that liquid, loses some of its energy because it's a collision, it loses some energy, and then it no longer has enough energy to bounce back off and fly back off and be part of the gas anymore. And so that can certainly happen, and it does happen with bodies of water. If a water molecule in the atmosphere collides with the body of water, loses a bit of energy, and then is now stuck in the pool of water, it becomes part of the liquid rather than part of the gas. So that certainly happens. That is still going to be cooling down the gas normally, because it would have to be a relatively lower energy gas molecule in order to become part of that body of water. If it was high enough, it might collide, give them some energy, but still have enough energy to fly off. So it's going to be the lower energy ones still that are condensing into that body of liquid. On the other hand though, even the lower energy gas particles have more energy than the higher energy liquid particles, so that process will also warm the liquid. So when you have condensation from a gas into a body of liquid, it will both cool the gas and warm the liquid. We can also get condensation onto something cold, and this is essentially the same as that first one. The lowest energy gas particles can be colliding and forming droplets of liquid, but that can be hastened, that can be sped up by having a cold object into which those gas molecules can collide and lose some of their energy. So a water molecule might hit the can, lose some of its energy, and now it's going to be stuck on that can with the other water molecules that have done the same thing, and together they form drops of liquid they have condensed onto the can. This will definitely cool the air down, because it is going to be the lower energy molecules again that collide and lose enough energy to stay on that can. Evaporation overall is a fairly slow process, waiting for just some of the molecules to get enough energy to be able to escape that liquid. Takes a while. As you've seen, if you watched a puddle on a hot day, it will take a while to evaporate. It doesn't just quickly get up to 100 degrees and all take off as gas. However, sometimes we want to get it there quicker, and we can certainly boil a liquid. And boiling is just the process of rapid evaporation. The idea of getting all of the liquid up really close to that boiling point so that all of those bonds can break and the liquid molecules can all leave as gas particles. So boiling is just rapid evaporation. And that's just continuing that same statement. Rapid evaporation is still evaporation, so the term evaporation still applies. Anytime a molecule leaves a liquid, or an atom or a particle leaves a liquid and becomes a gas, that is still evaporation, but we tend to use the word boiling just to refer to rapid evaporation. Now, one interesting fact is that we always have atmospheric pressure pressing down on the liquid. We've already met this. We've already talked about atmospheric pressure. What does that do to our boiling process? Obviously, it's part of it. If you boil a pot of water, that atmospheric pressure isn't changing the whole time. It's always pressing down on the surface. When boiling occurs, what's happening is that a bunch of the atoms in the liquid are suddenly getting enough energy to turn into a gas. And when you boil something, you generally give it heat at the bottom of the pot. So the water at the bottom of the pot is getting enough energy to turn into a gas. And so it does, and it forms a little bubble of water gas, right? Gaseous water. I'm actually going to jump over to the document camera just to try and hopefully illustrate this more carefully. So you've got your pot of water. Right? You have, so it's full of liquid water, and then you're applying heat here, and then suddenly these water molecules go, oh, we've got enough energy to become a gas. And so they do, they turn into a gas bubble. All right, so that's a gas bubble. But remember that there is pressure in the water. So the pressure here is 1 atmosphere. And then as you go down X centimeters, the pressure increases by rho g x. I'm using X instead of H for no reason. Rho g x. And so by the time you get to the bottom of the pot, the pressure is atmospheric pressure plus rho gx, plus rho g, whatever the depth of the pot is. And that pressure, remember, points in all directions. So that is pointing inwards on this gas bubble. It's trying to collapse the gas bubble. So the liquid molecules had enough energy to turn into a gas. They did so. They turned into a little gas bubble. That gas bubble is purely gaseous water. There can't be any air there because there was no air there to start with. Air can't magically get from above the water down to the bottom. So whenever you see bubbles in a pot of boiling water, they are purely water as a gas. Right? That's all they are. But the rest of the liquid is still pushing in on that gas bubble, trying to condense it. And if the pressure is high enough, then it will crush the bubble. All the water molecules that are around that bubble will push into it and collide with them and take that energy back off them, and the liquid will reclaim those molecules essentially. And the water that was in the gas bubble will turn back to a liquid and overcome that overcome that evaporation process. However, when the temperature of the water overall gets high enough, then the pressure inside that bubble will also be high enough, because remember that the pressure comes from the temperature of the gas particles. They're bouncing around and colliding into it, and into the surrounding water. And when they've got enough energy to overcome that surrounding pressure and get all the way to the top, because the gas is less dense than the water, so the gas is going to rise. That's why the bubbles go upwards. When they've got enough temperature to have enough pressure to overcome that water pushing back on it and get all the way to the top and escape into the environment as a gaseous liquid molecule or a group of them, then that's what the boiling process is. So to start with, you might notice some bubbles start to form and then they disappear, and then they start to form and disappear, and then they start to form, last a bit longer, and then they disappear, and eventually they form, rise all the way to the top of the water and escape. And that's because the temperature has got high enough that the gas, as it converts into a gas, the gas bubbles are high enough pressure to overcome that surrounding pressure from the water and escape off into the atmosphere. So there's this whole process going on. It's not just about giving them enough energy to convert from a liquid into a gas. It's about giving them enough energy to convert into a gas that has a high enough pressure to overcome the liquid pressure and escape into the environment. So with all of that in mind, you don't need to remember all of that detail that I just told you. Some overall idea of what I've just said would be useful, but you don't need to remember all the specifics, the whole exact process. And the reason we want to think about that is, if we go back to our slideshow, the reason we want to think about that is the question, can we boil water below 100 degrees Celsius? We said 100 degrees Celsius is the boiling point of water. That's the temperature we have to get it to turn it from a liquid into a gas. So can we make it boil below that? We said that pressure has to be high enough to prevent the bubble being crushed. Right? The pressure inside the gas, inside the bubble, has to be high enough that the bubble doesn't get crushed and can therefore escape the liquid. We can do this by heating the liquid so that the gas bubble starts with a higher temperature and a higher pressure, or we could decrease the external pressure. If we reduced that atmospheric pressure that's pushing down on the surface of the liquid, then the pressure at the bottom of the pot is also going to be reduced. And that means the gas doesn't need to be quite as high a temperature, quite as strong a pressure, in order to be able to get up and escape the pot of water. So you could theoretically lower that boiling point by reducing the pressure. And indeed, that's exactly what does happen if we reduce the pressure. Remember, we talked about the idea of a vacuum bell or a vacuum jar, where we can pump a lot of the air out and reduce the air pressure inside that jar. This little GIF here is from a video of some people doing exactly that. They put a beaker of water with a thermometer in it, they put it inside a vacuum bell, and then they pumped some of the air out. As they pumped the air out, the air pressure was decreasing, and by the time it got low enough, or at a certain point, it got low enough that the water could actually overcome those liquid bonds without needing any extra energy. They had enough energy to fly off into the air because there's now no pressure pushing it back into the liquid. So really, it is the atmospheric pressure that keeps water as a liquid in the first place. Right? The atmospheric pressure pushing down on the liquid says, no, you're going to stay as a liquid. If the atmospheric pressure is reduced, then there's nothing pushing on the water molecules to keep them there as a liquid, and so they will fly off, they will boil, they will evaporate off and become a gas. So you can absolutely boil things at low temperatures if the pressure is low enough, the atmospheric pressure is low enough. So could we then get something to boil at its freezing point? Could we have it so that water is trying to freeze because it's at 0 degrees Celsius, but also trying to boil because the atmospheric pressure is so low? Could we get that scenario arising? Absolutely, yes, we can. It is called the triple point of a substance. The triple point, because all three states can exist at once. The pressure is low enough that it could be a gas, it could also be a liquid, and it's cold enough that it could form a solid. So the triple point is the point where all three states can exist at once. For water, the triple point is 0.01 degrees Celsius, so cold enough to start forming a solid, but also warm enough that it could still be a liquid. But we have to get down to 611 Pascal, 0.6% of atmospheric pressure. We have to get down that low in order for a gas to be able to occur at 0.01 degrees Celsius. But it does exist, that point does exist, and if you have the right conditions, then you can cause it. Cyclohexane is a material or a substance which has a triple point that is closer to our obtainable pressures in our lab. And so here you can see a glass sphere, a glass sphere with some cyclohexane in it. They've lowered the pressure a little bit. It's pretty much at room temperature, but they've lowered the pressure a little bit, and that cyclohexane is trying to be both all three, a solid, a liquid, and a gas all at once. So you can see that it'll start to freeze over, and then it bubbles because it's boiling, and then it just turns back into a liquid and sloshes around. So it's doing all three different states all at once. And that's because they've found the triple point of that substance. Just as we saw with solid liquid phase changes, to vaporize a substance, you have to give it enough energy to overcome those bonds between all the liquid molecules. And how much energy that is will depend again on the substance it's made of. So for all of these things, for the specific heat capacity, which is the temperature change per joule per kilogram, for the latent heat of fusion, which is the amount of energy per kilogram in order to change from a solid to a liquid, or the amount that it gives off going back the other way. Or now the latent heat of vaporization, the amount of energy needed per kilogram to turn something from a liquid to a gas, or conversely, the amount of energy it gives off going back the other way. Those all depend entirely on what the substance is, what it's made of, what the atoms and molecules are that make up the substance. There's no way for us to calculate that easily. Instead, we just refer to big tables of data. So you just go online or go to your library, you look up a reference table for latent heats of fusion or vaporization or specific heat capacities, and you find the information needed. As I said, the latent heat capacity does vary a little bit by temperature, but because the latent heat of fusion or vaporization is just stuck at its boiling point or melting point, then that's just going to depend on the mass, not on the temperature, so we don't get that kind of variation. But we will generally give you any information you need in that regard. We don't expect you to go and look up and find these sorts of values. We'll give them to you for specific questions. But again, if you have some other scenario that you're considering, something you're wondering, something you just want to look up, then you will be able to find that information online or in libraries. There is occasionally a substance which will go straight from a solid into a gas. And that's because the pressure of the atmosphere is not enough to form that liquid. Remember, for the liquid water, we said the pressure was what was keeping it as a liquid. If you lower the pressure too much, it turns into a gas. And there are substances for which that is already the case at our atmospheric pressure. And the most common one is carbon dioxide. And that's why we have dry ice. Dry ice is when we cool it enough that it becomes a solid, but as it warms up, then the pressure is actually low enough that it turns straight into a gas. We don't get a liquid phase for carbon dioxide. You can get liquid carbon dioxide, but you have to increase the pressure a lot. It does not occur at atmospheric pressure. We'll often represent the phases as the phase triangle, which again, you're probably all familiar with, and so you probably don't need this, but there is the phase triangle. Sublimation, deposition. I don't know if I mentioned deposition on the previous slide, but that's just the opposite process when a gas goes straight into a solid. Condensation and vaporization between a liquid and a gas, and melting and freezing between a solid and a liquid. So that's the end of the first part of this lesson, which was just talking about phase changes and the energy needed there. I didn't go into too much detail on the energy needed for phase changes, just as I didn't when we were talking about temperature changes, and that's because of this next section of this lesson, which is on solving calorimetry problems. So all calorimetry problems are just energy conservation problems. That's all they are. We're saying there's some amount of energy that's going to be moving between them, and that's all heat is. Remember, heat is just the flow of energy, and we need to figure out which way the heat flows and what the result of that heat is, or potentially how much heat has been flowing. The rough guide, but remember, all problems are different. So just like all our mechanics problems, where we had discussion around what steps to take and what process to do everything in, it's going to be the same here. I can't give you step-by-step processes that will apply to every single problem because they are all going to be different. There might be some that you see and you've seen a very similar one, but there might be some where you've never seen anything else like it, and you need to be able to look at it and figure out, okay, where is the energy going? What's happening here? What phase changes are occurring? What temperature changes are occurring? And you need to work through that process. You need to be able to do that problem-solving process. That is what the physics is. If we just gave you step-by-step instructions and it applied for every single calorimetry problem, then it would just be math. There would be no physics. So the physics part of it is determining which way the energy flows, determining whether or not we're going to get any kind of a phase change or a temperature change or both. Sometimes we might not know that. Sometimes we might not know that until we're partway through the problem. If you're getting both, then it's often a good idea to break the process down into different steps. So you might say, well, step one is this substance heating up from some temperature to its melting point. Step two is it changing from a solid to a liquid at its melting point. And step three is heating up again once it's a liquid from its melting point up to some other final temperature. So you might find that it's easier to break it down into those steps. You then calculate the energy in or out of each substance during each step. And finally, you can use the energy to determine the temperature change you're looking for, or use the temperature changes to determine the energy, or whatever it happens to be that you're looking for. That step 4, I should have written it a bit more ambiguously. Use the information you have to find the information you're looking for. So there are a couple of problems here that we're going to work through. The first one is ice in water. 3 kilograms of ice at 4 degrees Celsius is added to 20 litres, 2 SF, of liquid water at 19 degrees Celsius. What temperature will the system end up at, assuming no energy loss? So that's our assumption, right? We've been told there's no energy loss, and that means that we have no heat flowing in or out of our system. So the total energy in our system must be conserved. The only way the energy in our system could change is if we had some heat flowing in or out, and we've been told there isn't any. Right? There's no indication of anything heating up the system, and there's also no indication, we've been told specifically that there is no energy being lost. So the problem is to solve that. Now, one thing I do want to just mention quickly is the idea of frames of reference. Now, when we were dealing with mechanics problems, frames of reference were a very common thing that I would refer back to. And I said, well, you've got to figure out, is it one-dimensional, two-dimensional, three-dimensional, which way are you going to do it, how are you going to set your frames of reference up, where's your origin, all of that kind of stuff. Obviously, we don't have quite the same thing here with phase changes, with calorimetry problems, with temperature changes. It's not quite the same, but we do still have to think about which way things are moving in our system. And so it's not technically the same sort of frame of reference as we had before, but you can still come up with some kind of definition of a frame of reference. And that's generally going to be saying that the temperature flowing from one substance to another is positive and going back the other way is negative, or something along those lines. So for this first scenario, this first problem where we've got liquid water and we're adding some ice to it, we can think about that as, here's our liquid water, and we're adding some ice. So we've got some ice and we're going to add our ice cubes into the liquid water. What that means is that we know, without even doing any calculations, we know that the ice must be colder than the liquid water. They did tell us temperatures, but it doesn't even matter. We know that ice has to be colder than liquid water. At least they're both at 0. But regardless, the temperature of the liquid water must go down, right? The temperature must go down because it's going to be losing energy to the ice, and the temperature of the ice must go up in order to come to the same temperature as the liquid. It's going to come up to 0 degrees, it's going to melt, and then it's going to turn into the same temperature as the liquid. So that tells us immediately that we need to be thinking about energy leaving the liquid, and so we might call that negative, right? So energy leaving the liquid we might call negative. And that same energy is going to go into the ice, so E negative, and the energy into the ice we might call E positive. But you've got to be careful here, because if we say that's negative, then that's positive, you might think that the energy is not being conserved. Because if you add up your total energy, one of them is losing energy, one of them is gaining, the total energy is positive, the total energy is constant. But depending on how you define that positive and that negative, you might end up with your total energy not being conserved if you do the maths wrong. And my point is that this doesn't really matter too much. The plus or minus doesn't really matter. The thing to be aware of and to be sure of and confident in is knowing which way that energy is going. So it doesn't matter if you call this positive. You might say the liquid loses it might loses an energy of 100 joules. It won't be 100, but I'm just using an example. The energy loss of 100 joules, and the ice gains 100 joules. And I don't have to write one as positive and one as negative, because I am aware that I am losing and I'm gaining, and I spelled gains completely wrong, but I'm aware that I'm losing from one and gaining from the other. So overall, I'm not going to have any change. So there's a fair bit to keep track of in some of these problems. This first one is relatively straightforward, but there is a fair bit to keep track of. So I actually recommend not relying on the numbers. Don't rely on the pluses and minuses. Rely on yourself to look at the scenario and keep track of what's happening. Okay, so the actual problem here is the liquid starts at 19 degrees C, and the ice starts at -4 degrees C. And we've got 20 litres of water, which we know is 20 kilograms, because liquid water is 1 kilogram per litre. And the ice, we have 3 kilograms of ice. So we've got 3 kilograms of ice, 20 kilograms of liquid water. The liquid water is at 19, the solid ice is at -4, and we want to figure out what temperature the system will end up at. So first thing, as I mentioned, is to think about the different steps, the different processes that are going to occur. So we should hopefully be able to look at this and go, right, well, step 1, the ice will come to 0 degrees Celsius. It'll go from 4 degrees Celsius to 0. Right? And that it can't change phase until it is at 0 degrees. So that's going to be the first step, is that it will increase to 0 degrees and the water will go down. We don't know what to, but it'll be less than 19 degrees C. It's going to lose some energy in order for that ice to come up to 0 degrees Celsius. Then the second step is going to be that the ice melts. Right? The ice melts. It's still at 0 degrees Celsius because it's a phase change, so there's no temperature change. But as it does so, the water is going to lose some more. So it's going to be even more smaller than 19 degrees Celsius. That's the second step. Now, at the end of that second step, we have liquid water at 0 degrees Celsius from the ice and liquid water at whatever temperature it's ended up at after step 2. But these are at different temperatures. And so now step 3 will be that the ice and the water, which is actually now liquid, the ice is liquid and the water, are both going to come to the same temperature. And obviously that means the water is going to lose a bit more energy and the ice is going to gain a bit more energy. So those are our 3 steps. And indeed, this same temperature is what we're looking for. That's the question we've been asked. What is that final temperature they come to? So by thinking about the process as these 3 distinct steps, it actually becomes a fairly simple process for us to follow through. We have also been told, I'm going to write them on here since I don't have both my screens showing, we have been told that the specific heat capacity of ice, now there are, technically the symbol is just a lowercase c, right? But because we've got ice and water, I'm going to write C of ice is 2040 joules per kilogram per Kelvin. The specific heat capacity of water is the one we already know, 4,180 joules per kilogram per Kelvin. And the latent heat of fusion of water, now you can write that however you want. I haven't specifically told you the rules for it. You might write it as an L for latent with a little F for fusion, latent heat of fusion. For water is 335,000 joules per kilogram. So those are the 3 bits of information we have, along with all of those starting conditions, 3 kilograms, 20 kilograms, minus 4C and 19C. So the first step is that the ice comes from -4 degrees Celsius up to 0 degrees Celsius. That's our first step. So how do we do that? Well, that's just a temperature change, which is just our specific heat capacity. So that says that if we have 3 kilograms of ice, and each kilogram of ice takes 2040 joules per kilogram per Kelvin, and we want to go up by 4 Kelvin, because we're going from -4C to 0C, which is a change of 4 Celsius, which is the same as a change of 4 Kelvin. If we want to go up by 4 Kelvin, then that means that we need this much energy for each of these kilograms 4 times. Right? So 3 kilograms times 2040, and this is where we need my calculator that I put down somewhere. So we need 2040 joules per kilogram. So for 3 kilograms, that's 6,120 joules. 6,120 joules will raise all 3 kilograms by 1 Kelvin, but we need to go by 4 Kelvin. So we multiply it by 4, and that tells us 24,480 joules. Right, so that is to warm up the ice from -4 Celsius to 0 degrees Celsius. And that was what we said was step 1. Step 1 was moving ice from -4 up to 0. But during that step, that energy has to come from the water. So that means if the ice has gained this much energy, it's gained 24,480 joules, then the water, the liquid water, must have lost that many joules. So our liquid water loses 24,480 joules. If it didn't, if the ice just gained that magically from nowhere, then the energy for our system has gone up as a whole, which means it must have come from somewhere because of energy conservation. We can't create energy. So the energy must have come from somewhere. If we had a heating element or a fire or some kind of system that was getting energy poured into it, that could happen. But we don't. We've got an isolated system where there's no energy going in or out according to what we were told. So that means that we can't have that energy just coming from elsewhere. It has to come from the liquid water. So the liquid water must go down by 24,480 joules. And given the liquid water is 20 kilograms, so we know that C of water is 4,180 joules. And we know that the mass of the water, the liquid water, is 20 kilograms. Then that means that we know how much energy there was. Sorry, that should say per kilogram per Kelvin. We know how much energy there was. We know how many kilograms there were. And we know how much energy each kilogram needs to move by 1 Kelvin. So what we can do is we can say, well, these two bits of information, they tell us that the energy for 1 Kelvin change of our 20 kilograms of water is going to be 4,180 times 20. So it's going to need 83,600. So 83,600 joules to move by 1 Kelvin. That's how much energy we would need for our 20 kilograms of water to move by 1 Kelvin. It's just 20 times the amount for 1 kilogram. That makes perfect sense, hopefully. So 83,600 will move by 1 Kelvin, but we were only losing 24,480. So that means that we're not going to lose a full Kelvin. We're going to lose around about a third of a Kelvin, or somewhere between a third and a quarter of a Kelvin. And so to figure that out, right, you could actually look at the units if you wanted to, if you weren't intuitively sure, but we're losing this much energy, and this much energy results in a change of 1 Kelvin. So we go 24,480 divided by our answer will tell us that we have gone down a change in temperature of negative 0.29 Kelvin. So I added the negative in now because I'm moving into a temperature scale and I know that it's dropping temperature because we know it's a losing temperature. But you see, I didn't include the negative when I was just doing my working because, again, keeping in mind the physics, keeping in mind that we know the water is losing energy means we know it's going to cool down. So our change in temperature is 0.29, or about a third of a Kelvin. Why did I know to take this energy and divide it by this one? Look at the units, right? The units, we've got joules, and we divide by joules times Kelvin to the negative 1. The joules cancel. We're left with 1 over Kelvin to the negative 1, but 1 over Kelvin is just equal to Kelvin. Right? Whereas if we did it the other way around, if we took 83,600 and we divided that by 24,480, we'd end up with joules per Kelvin divided by joules, which is Kelvin to the negative 1. And that's not a temperature change. So that wouldn't give us the right result. The other things you could do would be to multiply them. You'd get joules squared per Kelvin. Again, not useful, right? So you can actually look at the units, say we want a temperature, what do we need to do? Well, if we take this and multiply it by kilograms, they cancel out. Right? So we're left with joules per Kelvin. And then if we divide joules by joules per Kelvin, we're left with Kelvin. So you can actually use the units to figure that out. But the actual formula is that the specific heat capacity is equal to the mass times, the energy, setting you off on the wrong foot. Energy is equal to the mass times the specific heat capacity times the change in temperature. So if you wanted to use that formula, you can, but as I said, you can usually just think about it. Right? The reason I didn't put that formula down, I may have gone back and added it to the slides, but the reason I didn't start my problem with that formula is that you don't really need it. If you think about what specific heat capacity means, you can pretty much figure out these problems. It means you need that much energy per kilogram to go up by 1 Kelvin. If we've got 20 kilograms, then 20 times that, we need this much energy per Kelvin. Right? You need that much energy to go up by 1 Kelvin. We only put in that much, or lost that much, so we lose about a third of a Kelvin, which as we saw was 0.3 of a Kelvin. And if you do that kind of thought process, that's another way to check. If you look at that and say, well, 83,000 would lose us a whole Kelvin, we've only lost 24,000, that's going to be around about a third of a Kelvin. If you get a value out that's not about a third, then you know you've done something wrong and you can double check. But about a third, 0.29, good. So that means at the end of step one, we have the ice is still solid, but it's at 0 degrees Celsius, and the water is now at 19. It started at 19 degrees C, but it's dropped by 0.29. All right, so it's dropped by 0.29. So we go 19 minus answer, we get 18.707. I'll go 18 degrees C. I'm including extra significant figures here because I'm still in the working process. You don't round until the end. If you round in the middle of your working, then it can end up adjusting your final result. You can end up incorrect. So the whole point of that step one is to get the starting conditions for our step two. So I'm just grabbing a new sheet of paper. So starting conditions for step two. So for step two, we want ice to change from a solid to a liquid. The temperature is not going to change, but the ice is going into a liquid. We have 3 kilograms of ice, and we are told that the latent heat of fusion is 335,000 joules per kilogram. So if each kilogram needs 335,000 joules, then for 3 kilograms, we just need 3 times that much. So the energy needed, the energy to melt the ice, is going to be 3 times 335,000 joules. And so, again, just grab our calculator, 3 times 335, Mr. Zero, is 1,005,000 joules. 1,005,000 joules. And where does that come from? Again, we know that that has to come from the water, from the liquid water. This is going to be liquid water as well now, but from our original 20 kilograms of liquid water. So that liquid water is going to change by some temperature amount as well, and that's what we're trying to figure out now. So what is that temperature change going to be? The equation that we had before is still the same. We said that 20 kilograms of water is going to take 83,600 joules to drop by 1 Kelvin. And now we're losing 1,000,005 joules. So how many kelvins is that going to drop? Well, if it takes 83,600 for each Kelvin, and we're losing 1,005,000, then we're going to drop, other way around. I've done it back to front, haven't I? 1,005,000 divided by 83,600. I think I just did that back to front, but I knew it would drop by more than a Kelvin because this is much bigger than that. So I immediately knew I'd done the calculation back to front. So we've got 12. So our change in temperature is 12.02153. And we know it's a drop. We know it's a drop in temperature because it is losing that energy to the ice as the ice converts to a liquid. Now remember that at the end of phase one, or step one, we had a temperature of only 18.70718. It had already dropped a third of a Kelvin, or a third of a degree Celsius, from its original temperature, and now it's dropping another 12.02153 Kelvin. So that means that our temperature of the liquid water, so the liquid temperature at end of step two, is going to be 18.70718 minus 12.02153, which is 18.70718 minus answer 6.68565 degrees Celsius. So that is the temperature of the liquid water at this point. Of course, everything's liquid water, but I'm still going to refer to it as the ice and the liquid water just to keep those two sort of groups of water molecules separate in our heads. So at the end of step two, we now have 3 kilograms of liquid water, which was the ice, at 0 degrees Celsius. Remember that the temperature doesn't change. So we've got, that's at 0 degrees Celsius. And we've got 20 kilograms of liquid water, which was always the water, at 6.68565 degrees Celsius. So step 3 is that these two bodies of water will come to thermal equilibrium. They'll exchange energy until everything's all at one average temperature. So how do we do that? So this bit is actually a little bit, the maths is probably slightly harder than what I would normally get you to do in this course, but it's certainly not too difficult to do. What you need to think of is that the energy needed for, so this is for step 3, the ice is going to go from 0 degrees Celsius up to some final temperature X degrees Celsius. And the water is going to go from 6.68565 degrees Celsius down to that same X degrees Celsius, because we've got to both come to the same temperature. And so all we've got to do is find the amount of energy that this gains that makes it the same as the amount of energy that that loses. And remember that this is 3 kilograms and this is 20 kilograms. So now we've got 3 kilograms. So for the ice, we have 3 kilograms and it is 4,180 joules per kilogram per Kelvin. So that means that we're going to have 3 times 4,180, we're going to have 12,540 joules per degree temperature change. For the liquid water, we're going to still have the same as we had before, which was this 83,600 joules per Kelvin. 83,600 joules per Kelvin. As I said, this last step is actually a little bit beyond what I would normally get you to do. So if you've followed everything up to this point and you're starting to get a little bit confused here, don't worry too much about this final step. As long as you could follow those first 2 steps, that's the sort of level I would expect of students taking this course. But if it all made sense and if this bit makes sense, then it does just open up a slightly wider range of calorimetry problems that you can tackle. So 83,600 joules per kilogram, and then joules per Kelvin. And so now we know that the amount of energy that these give off, that the water gives off, has to be the amount the ice absorbs, and we know that this is how much energy will cause that change in temperature. So the amount of temperature change for the ice is going to be X. It's going to go up by X degrees Celsius. So we know that X is equal to 12,540 times, sorry, the other way around. E is equal to 12,540 times X. I'm going to write that again because I made a mess of it. The energy needed is 12,540 joules per kilogram, joules per Kelvin. I keep saying joules per kilogram because of the specific heat capacity. Joules per Kelvin, and we're going up by X kelvins, right? So the energy needed is 12,540 times a step of X kelvins. The energy for the water to go down from this value to X is going to be 83,600 joules times the temperature change, which is 6.68565 minus X. No, because it's dropping from that to X, so the temperature change is actually that much. And we know that those two energies have to be the same, because the amount of energy that this loses by dropping this much is going to be the same as the amount of energy that that one gains. And so now it's actually just a really simple problem where you've got this, this X is the only thing we don't know, because we know that these two energies have to be the same, so we can solve for that X. But at this point, if you tried to solve that, you'd probably find that it doesn't really work very well, and that's because we've got the X being positive here and positive here, but this is a negative temperature change and a negative energy drop. So you might find that as you rearrange it, you need to add some negatives in. And again, just keeping in mind that we know that the system is going to come to equilibrium somewhere between 0 and 6.7 degrees Celsius. Right, the water has to cool down, so it has to be less than 6.7. The ice has to heat up, so it has to be more than 0. So you would find, hopefully, that it ends up in that range. So if we rearrange this, Now, if we rearrange this, what you would find, might leave that as an exercise for you. As I said, if you're confused by this step, forget about it. If you're not confused, have a go at rearranging and solving for x. And what you'll find is that x is equal to 5.8137 degrees Celsius. And that is our final temperature, which we would write as 5.8 degrees Celsius, since we are not, we are only going to 2SF. So hopefully that wasn't too confusing. That last step, as I said, feel free to forget about that last step if you want. I know I started to confuse myself on occasion. So that is the calorimetry process for a relatively complicated problem, even though it seemed simple to start with. Like, the idea of the scenario is simple. So just going back to our slide, the idea of the scenario was simple. We had some ice, we chucked it in some water, and we watched what happens. That's a very simple scenario, but the calculations ended up getting a little bit messy. So certainly I would expect you to be able to look at this and describe those 3 steps. That's not beyond us at all, but the maths of that very last step you might find a little bit beyond you, but certainly still accessible for the majority of you. So hopefully you can follow that. Hopefully you definitely could follow through the first 2 steps. Repeat those first 2 steps if you're at all confused. Have a go at them. Try and do those first 2 steps. You need to be able to do them. That is what I expect of you from this course. As usual, I do have the solutions to the question in the slides. So I've walked my way through it all here. In the slides, I do keep track of the positive and the negative, keeping in mind positive means it's gaining energy, negative means it's losing energy, so keeping in track all of that. And we get to the same result of having the final temperature of 5.8 degrees Celsius. That is the final temperature of our system. Just to recap that whole process, step 1, the ice gained 24,480 joules from the liquid water to bring it to 0 degrees Celsius, which decreased the water to a temperature of 18.7 degrees Celsius. In the second step, the ice needed to gain 1,005,000 joules in order to change phase to a liquid. That came from the liquid water, and that dropped the temperature of the liquid water to 6.7 degrees Celsius. In the third step, the ice is now liquid water at 0 degrees Celsius, and the originally liquid water is still liquid water, but it's now at only 6.7 degrees Celsius. And in order to come to thermal equilibrium, they would both lose equal amounts of energy. Sorry, the liquid water would lose an amount of energy that was equal to the amount of energy the once ice water has gained in order to come up to that temperature, and that happened at 5.8 degrees Celsius. Just as a little extra step here, I often remind you not to round until the last step, until you're presenting your result. Let's see what would happen if we did round. If we did this whole process and rounded to 2SF every time, then what would happen? In the first step, the ice increases to 0 degrees Celsius, but the water, because it decreased to 18.7, would still be 19 degrees C to 2SF. So the water temperature wouldn't have changed, and immediately that should be setting off some alarms, and you're going, hey, hold on, how can we have lost energy and still be at the same temperature? We can't, as we know, but because it was such a small temperature change, our 2SF rule would mean that we are still at 19 degrees C. Step 2, the ice is 0 and it wants to change to liquid water. The liquid water would now lose significant energy and it would end up at 7.0 degrees C. That is if, again, we were rounding to 2SF, which we shouldn't do, but for the purposes of explanation or justification, hopefully, we would end up at 7.0 degrees Celsius. And the final step, we now have 3 kilograms of water at 0 and 20 kilograms at 7. They would come to thermal equilibrium at 6.087 or 6.1 degrees Celsius. And our actual result was 5.8, so it's not hugely different. There's no huge difference there. 6.1 to 5.8 is only 0.3 of a Celsius, but the point is that it is different and it is incorrect within our significant figures. So by rounding to the significant figures the whole way through, you have ended up with an incorrect result. So this is hopefully just a reminder and a bit of justification, and hopefully something you'll remember as you're doing any problems. Don't round while you're working, only round when you present your final result. And if you were then going to take that final result and do some more working, you should hopefully continue with the unrounded result. So if we were going to take that 5.8 degrees C and plug that into a new equation, maybe we go and add that 5.8 degrees Celsius water to some other system. hopefully you would remember to take that unrounded result and you would actually take the 5.8157 degrees Celsius, not the rounded value of 5.8. That said, when you're doing a test or an exam, I'm not worried about the rounding. If you don't want to write out 10 significant figures every time you're doing a step of the calculation, I will be fairly lenient, but I do want you to be aware of that. And certainly for assignments and things where you're projects where you're taking a bit more time for yourself, you're not under that time pressure, I would expect you to do it properly and use the unrounded values for your working and only round to present your final result. The next question, I'm not actually going to do this one on the document camera. I'm just going to talk it through. That's because the answer slides I've got are fairly comprehensive and hopefully it will all make sense anyway. But as usual, feel free to ask questions. If there's any bit of this process you're not sure about, jump onto the forums or into the tutorials, but do feel free to come and ask questions. So remember that our process is to think about the system first, think about what's happening, break it down into some steps, and then calculate the energy changes. If you go straight to the math, straight to those calculations of energy changes, don't think about the system at all, you can end up with some weird results and numbers that are completely wrong, but you don't think about it because you haven't done that physics to start with. This question is about a bar of milk chocolate being melted with some cold milk in order to make a hot chocolate. You have a 125 gram bar of milk chocolate. It's at room temperature of 21 degrees C. You have 250 mils of cold milk at a temperature of 4 degrees C. You put both of these into a small cast iron pot, which has a mass of 1.5 kilograms and is also at room temperature of 21 degrees C. You place the pot onto a stove top, which delivers 260 watts to the pot. How long will it take for all of the chocolate to melt? So there's some more info on the next slide, which I'll get to in a moment. But first of all, just think about this system. Think about the scenario and the system. What's going on? We have a pot, we have a chocolate bar, and we have some milk that we're putting into the pot. So all three of those things are in our system. The pot with the milk and the chocolate are all in our system. And we have a stovetop, which is delivering 260 watts. Remember that watts is just joules per second. So 260 joules per second. So this stove is delivering 260 joules per second to our pot, and it's going to raise the temperature of the pot, which is going to raise the temperature of the milk and raise the temperature of the chocolate, and we want to melt the chocolate. So that's the next slide will specify that question, but that's what the process is going to be. So that means that we don't have a conservation of energy like we saw in the previous problem. In the previous problem, when the ice gained some energy, we knew it came from the liquid water. Here, all the energy that everything gains is going to be coming from the stove, from the element. Now, the things start at different temperatures. The milk is colder than the chocolate and the pot. And so you might think maybe we should start by getting the milk and the pot and the chocolate to all come to equilibrium. Maybe we should do that. You could, but it's a whole lot more work and it doesn't actually change the outcome. All that happens is the milk gets a little bit warmer, the chocolate and the pot get a little bit colder, and everything starts at one temperature, and you then do your energy calculation. But it doesn't actually make any difference. And if you think about the real world system, you put the cold milk and the room temperature chocolate into the room temperature pot, and you immediately turn the stove on. They don't all come to the same temperature straight away. They would take some time to do that, but if you start pumping the energy in straight away, then they're never actually going to reach that same temperature. Instead, we're just going to be heating them straight away. And what we can actually do is think about the energy each one needs independently and then just add them all together. The energy that the pot needs to get up to the temperature we want, that the chocolate needs to get up to the temperature we want and to melt, and that the milk needs to get up to that temperature. You can think about each of those three processes separately, figure out how much the total energy is that all three need to get to that temperature, and then you can just figure out how long that would take based on the watts, because we know it's 260 joules being provided every second. So hopefully that all sort of makes sense, right? Just think about the scenario, think about those steps involved. In this case, the steps aren't linear, they aren't one after the other, they aren't chronological steps. So we're not saying, right, first of all, the pot's going to heat up, then the chocolate's going to heat up, then the chocolate's going to melt, and then the milk is going to heat up, because they're all going to be happening at once. So it is sort of in that sense, in time sense, it's one step. But what we can think about instead is the components as different steps. The pot heating up is one step, The chocolate heating up is another step, the chocolate melting is another step, and the milk heating up is another step. But they're all just sort of happening together at once, because we don't need to worry about the interaction. It's not like the milk heating up is giving some of the energy to the chocolate heating up. In the ice water one we just saw, they did happen. The ice heating up did take energy off the water. But in this one, they're all getting energy from outside. So all we care about is how much each one needs. So we can treat each one separately and then just figure out the total energy needed. So here's all the information. The melting point of chocolate is 31 degrees C. The latent heat of fusion of chocolate is 31.2 kilojoules per kilogram. First of all, first thing you should note as we're writing these down, kilojoules. Kilojoules is 1,000 joules, so 31,200 joules per kilogram. Specific heat of solid chocolate is 1.6 kilojoules per kilogram per Kelvin. Again, immediately convert that into joules per kilogram per Kelvin. That should be one of the first things you do as you write these values down. Density of milk is 1,030 kilograms per cubic meter. Specific heat capacity of milk is 3.77 joules per kilogram, per gram per Kelvin. Again, notice that difference. 3.77 joules per gram per Kelvin. You should immediately realize that we need to divide by, multiply by 1,000 to convert that into per kilogram instead of per gram. So we get 3,770 joules per kilogram per Kelvin. And finally, specific heat of iron is 450 joules per kilogram per Kelvin, and that's already in SI units. So there's all that information, and hopefully what you've realized here is we've been given the density of milk, and I'm going back a slide, we were given a volume of milk, 250 mils, which is a quarter of a litre, and you'll remember that there's 1,000 litres in a cubic metre, so we've got a quarter of a thousandth of a cubic metre, so you can do a unit conversion. Of course, if you're working at home, you're allowed to use things like Google and other software to convert volumes and things. You don't have to rely on memory, but you should hopefully be capable of converting into kilograms from mils with that. So as I said, all three parts of our system are gaining energy. The stove elements is providing it, but it's going to be distributed to the pot, the milk, and the chocolate. In reality, the pot is going to warm up a bit faster than the chocolate and the milk, but we're going to make the assumption that they all sort of stay roughly together as they approach that melting point of chocolate in terms of temperature. So we're not going to worry about the technical distribution, like the pot getting warmer first and then the chocolate and the milk warming up after that. We're just going to assume they all sort of stick at roughly the same temperature as they approach 31 degrees Celsius. So what we're concerned with is the total amount of energy the stove will need to deliver, and then that will tell us how long it takes because we've been told the power rating of the stove. So what we want is for everything to come to 31 degrees C and for the chocolate to melt while it's at 31 degrees C. And once we're at that point, we're done. So firstly, the iron, 1.5 kilograms of iron, it's going from 21 degrees C to 31 degrees C. So just a 10 degrees C jump. The milk is going from 4 degrees up to 31 degrees C. So that's another one of our steps, is the milk increasing in temperature. And the chocolate, 125 grams of chocolate going from a solid at 21 degrees C to a solid at 31 degrees C, and then from a solid at 31 degrees C to a liquid at 31 degrees C. As I said, we can calculate each part and then just add them all together. So the energy needed for the pot to increase by 10 degrees C is just the mass, the 1.5 kilograms times how many joules per kilogram times how many Kelvin, and that gives us 6,750 joules. The milk, first thing, as I said, is to figure out the mass of the milk. We have the volume of 250 mils, which is a quarter of a litre to 0.25 of a litre, and a litre is 1,000th of a cubic metre, so 0.25 times 10 to the negative 3 or 2.5 times 10 to the negative 4 cubic metres. You should be confident with that sort of unit conversion at this stage of the course. With a density of 1,030 kilograms per cubic meter, we get a mass of 0.2575 kilograms. And at this point, hopefully your brain says, oh, well, a litre of water is a kilogram. A quarter of a litre of water would be a quarter of a kilogram. Milk here is slightly more. Instead of 0.25, it's 0.2575. So that makes sense. Milk was slightly more dense, should be slightly more mass than there would be if it was water. So hopefully that sort of process in your brain is going on. Right? This is the sort of thing that physicists and teachers don't often mention. We just go, oh, there's the value. But this sort of little thought process is going on in the back of our minds. we see this value, then we go a cup of water, 250 mils would be 250 grams. So a cup of milk being just slightly more than that makes sense. And then the energy to calculate, energy to increase from 4 to 31 degrees C is just a 27 Kelvin jump. And the same process as we had before, the mass times that amount of energy per kilogram per Kelvin times the number of Kelvin that you're changing gives us a energy requirement of 26,210.925 joules. So now we know how much energy the milk and the pot both required. The last one is the chocolate. First of all, we have to increase the temperature, and that is just the specific heat capacity when it's a solid times our mass of 0.125 kilograms times our change in temperature of 10 Kelvin, 21 up to 31, and that gives us an energy requirement of 2,000 joules. So 2,000 joules will change it from being 21 to 31 degrees C, but still solid. And then once it reaches 31 degrees C, we have to melt it. Now there's no temperature change, but we know that it takes 31,200 joules per kilogram. We've only got 0.125 of a kilogram, so that means it's 0.125 of that 31,200, which is 3,900 joules. So now we've got the energy for each part of our process, each step of our process, which remember wasn't chronological steps, it wasn't one after the other, they were all happening at once. Well, the chocolate was warming and then melting, but they were each happening, but they each just took some energy, and we can just add them all together because we didn't really care about where the energy was flowing when, we just cared about that total amount of energy to get us to that final point. So we can take those four energies we just calculated and we can add them all together, and we see that the total energy needed is 38,860.925 joules, and that will get us from our original scenario to the final scenario of having a melted block of chocolate in the now warmed milk and the warm pot. But the question, of course, was asking how long it would take for this to occur. We are told that the stovetop is delivering 260 joules per second. We just said that we need 38,860 joules in total. So if we have 38,860 joules and it takes 260 joules per second from the stovetop, that is going to take us 149.465 seconds, or 150 seconds, which is 2.5 minutes from turning it on to having that melted chocolate and the pot and milk and everything all being at the same temperature. So that is the answer to the question. Again, I've put that part 2 in the wrong place. I'm not sure why that is there. I apologize. But again, the rounding would produce a slightly different result. If you rounded each of those four values and then added them together and then used your rounded total energy to divide by 260, you might find a slight change. It probably wouldn't be as big as the change we saw in the previous question, but it would still result in a change potentially. So do keep that in mind. And that is the end of this lesson. So we talked about phase changes, and then we went through 2 different examples. One other thing that I do want to mention that isn't in the lecture slides and isn't really in the course materials, but is just something to think about that we sort of touched on almost. We talked about evaporation as being the idea of some of the water molecules leaving a pool of water even though it wasn't at 100 degrees Celsius. And we've also talked about the idea that water, as it freezes, there are still some ice crystals between 0 degrees C and 4 degrees C. So it doesn't instantly all change phase to liquid water at 0 degrees C and then all of a sudden just be water from 0 upwards. We see that there is this gradual flattening, this smoothing out of the transition process. So once a solid block of water has melted or mostly melted, then some of the particles will start to get a bit more energy, and it can get up to 4 degrees C before all of the ice crystals finish melting. That was what we talked about with the ice-water density process. So my point here is that when we do a lot of these problems, we do assume that that temperature change doesn't occur at all while the phase change is occurring. That was one of the rules we said. When a phase change is occurring, all the energy is going into changing the phase and none of it into changing the temperature. And that is, on the whole, pretty close to being true. Right? If you melt a 4 kilogram block of ice and then you heat that 0 degree water all the way up to 20 degrees Celsius, and you use your latent heat of fusion and your specific heat capacity of liquid water to calculate that, that's going to be pretty much correct. In reality, if you watch the process on an atomic scale, what you would find is that not quite all of that energy, that latent heat of fusion energy, had gone into the system when it started increasing temperature, but it would still use a bit more of the energy as you pour it in to finish breaking all those crystal bonds and continue heating up the temperature. So there's a little bit of overlap. As it's mostly water, once it's mostly liquid, you still get a start of an increase of temperature change, but you still use some of that energy to finish that phase change. So there is technically a slight overlap, but as I said, as long as we're dealing with temperatures that move away from our boiling and melting points significantly, then we generally end up at a reasonable approximation. The maths are pretty close, the results are pretty close. But for a question like that one we just had with the chocolate, we said the chocolate getting to solid, getting to its melting point and then all melting, and that was our end point. That wouldn't really happen, because when you got to that melting point and you started putting energy in to melt it, then most of the chocolate would melt, but the temperature would start increasing before it had fully melted. And so you have little bits of solid chocolate still in the system, and the temperature starting to go up beyond 31 degrees C. So it is useful to be aware of things like that, because it might actually take longer in the real world, because that chocolate won't completely melt until it's beyond that 31 degrees C. There will be little lumps of solid chocolate continuing, persisting after that melting point. So just that slight variation between real world physics and theoretical physics is just still useful to bear in mind. And it's something that we already talked about when we talked about mechanics. And so just being aware that that is still an issue, and you may still need to think about that in certain scenarios.